Hi, everyone. We're going to get started now. Hi. Hi. Thank you for coming today. That's really great. Thank you for coming for our first MOGE discussion series session. We hope you enjoy. Just a bit of background. We want to thank our series sponsors, so Arup, Atkins Realis, Cowie, GCG, Mark McDonald, and Russell Geotechnical Innovations. Thank you. The motivation for this discussion series is to create a platform to pass on current industry knowledge, help identify what we can do next, and primarily to have engagement between early, mid, and late career professionals, which is what we think you'll all get out of today and the following series. A very brief kind of overview on what we're planning. So it's going to be a series full of 15 to 16 sessions. We plan to host them in person and online. We hope that we can also have some sessions outside of London, and there'll be more info afterwards on the following two sessions. So we really encourage audience participation. There'll be a microphone going around later, and we are using Slido. So if you log into or open Slido on a browser, put in the code, and we've got a tester poll. I can't remember what we said. Right, so Slido kind of code is up there in the top right hand corner. So our opening question is, how do you pronounce MOGE? So MOGE, that's how I pronounce it though. MOGE, MOGE, and my pronunciation, MOGE. So vote ahead and we'll kind of get an overview on this because I think everyone has a different answer. Right, I'm going to hand over to Pishan now as the chair of session 1. Thank you.
We'll put the results up for at the end, but for anyone interested, yeah, thanks Palak, co-chair of the current early career group of the BGA. And yeah, today's first session really is sort of the first in this big initiative from the early career group, as well as the authors of the Manual of Geotechnical Engineering. And we're trying to bridge this gap between the early stage professionals, which is why the session will be hosted by a series of ECG early career group hosts, with very esteemed established members of our industry and the authors of the book. And today, I'll just wrap up this little brief introduction. We've got Professor John Burland, Dr. Jackie Skipper, and Tim Chapman as our speakers. Emeritus Professor John Burland from Imperial will speak first on the selected chapters 4, 7, and 40, but they're very much a guidance for discussion rather than a focus of the technical content we'll go through. So we really do hope we can encourage audience participation. After Professor Burland, Dr. Jackie Skipper, Senior Consultant at Geotechnical Consulting Group, will follow, and then Tim Chapman. I'm sure none of our 3 speakers will need any introduction, but at BCG now and former director at Arup. And then after the presentations, we'll round off with hopefully lots of audience participation, questions on Slido or in person, and a discussion with the panel. So with that, I'll hand over to Professor John Burland.
Oh, thank you very much, and thank you for inviting me. It's a wonderful turnout. Well done. Terrific. I have spoken in the past to a younger group, but I think that they've all gone old now. So this is a special lot of youngsters. So you'll take over. I thought that it'd be worth starting off with the geotechnical triangle because I found geotechnics and soil mechanics in particular as an undergraduate an impossibly difficult and incomprehensible subject. There seemed to be so many arbitrary rules, and some of them were empirical and some of them were somewhat dubiously analytical. And I found it a most boring subject, to be honest. But after graduation, the professor was given some money to do some research actually on silt pressures behind retaining walls. And he looked around and said, would you be interested in doing this for a year? And I thought, well, yeah, that'd be interesting. I've always wanted to do a bit of research. And once I got into it and began to read around the subject, I got absolutely fascinated by geotechnics, but it was very badly taught at an undergraduate level. And that's really what got me into the subject. And I spent ages reading up to Zagi and Borshlev and people like that. And I just found it intriguing. So that's why I'm here where I am. Geotechnical triangle. Well, first of all, it is a difficult subject. And I know from working with other civil engineers and in particular structural engineers that it's often regarded as a sort of black art. And I used to think that this was probably due to the fact that it was the nature of the ground, that it was a three-phase material and therefore provided by nature and therefore a difficult material. And I always thought that that was the reason why it was thought by many practitioners, civil engineers and structural engineers, as being a kind of black art, witch doctrine. But when I began to actually start teaching here, I studied the work of Terzaghi in particular and Peck, and I came to the conclusion that actually the main problem wasn't the fact that it is an unusual and difficult material, particulate with water pressures and so on it. That wasn't the real problem. I felt that the real problem was that there were a number of aspects of geotechnical engineering which are involved in tackling a ground engineering problem, and that they got very confused. The various disciplines, the various aspects of geotechnical practice got into a mess. And as a result of actually being asked to write a paper on the teaching of geotechnics, I then settled down and thought, well, I've got to try and get this sorted out in my mind. Why is it apparently such a difficult subject? And so I did spend a lot of time, particularly looking at Terzaghi's struggle to make it a respectable discipline, soil mechanics, and Peck and various other great figures in the past. And I came to the conclusion that there are at least 4 distinct aspects of soil mechanics or geotechnical engineering, which are vital. And that's where the soil mechanics or the geotechnical triangle came from, those 4 aspects that appeared to me to be absolutely fundamental. And the first one is the ground profile. The second one is observed and measured behavior of the ground. And of course it is a difficult material to capture with equations and so on. The third area is how you model, how you develop analytical models for tackling geotechnical problems. And the fourth one is that it's riddled with empirical procedures. Lots of empiricism inevitably comes in to geotechnical engineering because you're dealing with a natural material. I really developed the triangle around those four aspects involved in tackling any ground engineering problem. And so there are, and I felt that that could be identified and laid out. It'd be much easier for students to find out where they were going and what the subject was about. But subsequent to that, I also discovered that it's just as applicable to practice. It's a very useful concept, the triangle, when you're dealing with a practical problem. So let's have a look at the triangle. I think I'm going to have to work out how to use this now. Is that right? Yes. And to move the pointer there. Okay. So we start off with the ground profile, and that's at the top of the triangle. And then lower down, we have the measured behavior. I was hoping I might get the full triangle, but I'm obviously not. Perhaps oh, there we are. We have the measured behavior down here across an appropriate model that we use for analyzing the problem, making predictions. And then in the middle, we have empiricism. And in a subject as challenging really as geotechnics, there is an inevitably a lot of empiricism and experience. And I used the word well-winnowed experience, really based on some work of Tazagi, who was a very keen geologist, incidentally, a very expert and knowledgeable geologist. And he was trying to lay the foundations of soil mechanics. And he spent 2 or 3 years getting case records. And he, in one of his lectures that he gave to I think an early international society, he talked about the history of the development of the subject. And he said after 2 years' work, he brought all his case records back to his study, and he found great difficulty in making any sense of them at all. There seemed to be no coherent message coming through. And he said, really, instead of really valuable stuff there, he found, instead of a lot of wheat, he found a lot of chaff. Now, winnowing is getting rid of the chaff. And that's where I coined the expression well-winnowed experience. It's experience which is relevant and well proven and well tested, and the basis of it is understood. So that's really where the triangle came from. So we can go through the various activities that are involved, and the first one is the ground profile, and by that it involves obviously it's generated by a geological process, and we need to understand its genesis, where it came from, how it was formed. That is absolutely critical. And then there is the other aspect of it, is the ground exploration and the description. Now, I've tried to keep numbers out of describing a ground profile. As we'll see in a moment, it is absolutely fundamental to tackling any ground engineering problem, is to have a clear record of the ground profile that you're dealing with. And it's not necessarily quantified, but there are 6 aspects of the ground, of an element of ground that are important. And I've sort of listed them. I had a mnemonic, which is MCCSSOW, which stands for MCC, so wonderful. But if you don't believe that, the English are good at cricket, then you can say MCC, so what? But those letters, M stands for moisture condition. The C first C is the colour. The second C is the consistency. The first S is structure. Is it fissured or not, and so on. And the second S is the soil type. And then at the bottom, you've got O, which is the origin. And very importantly after that, you have W, which is the groundwater. And those are the 6 elements that make up each sort of strata in a ground profile. And you don't necessarily have to put numbers to them. It's absolutely vital to get your ground profile described in that way. So in summary, what you need to know is what is there and how did it get there? And the numbers come later. Now, I'm going to give a case record in a little while, but in my experience, 9 times out of 10, major design decisions can be made on the basis of a good ground description, of a good soil profile, without putting numbers on it. Also, again, in my experience, in 9 failures out of 10 that I've been involved with, it's been due to a lack of knowledge about the ground profile. So the ground profile is incredibly important, very, very important. Then we come to measured behavior, which is, that's an activity that involves measurement. It might be lab testing of a simple or an advanced nature. It might be field testing. It might be penetrometer testing or plate loading testing. But there's this element of measurement of behavior in it. And that's a very important aspect of understanding the soil behavior. So that's the bottom left-hand corner of the triangle. And then we come to appropriate modelling, which is here. A model can be, it's really an idealization. A model is a simplification of reality, which enables one to carry out an analysis of some sort in order to take the design forward. So by modelling, I would mean the process of idealizing and simplifying our knowledge of the profile, which you've got from looking at the ground profile, simplifying our knowledge of the real world. And we have to assemble these idealizations into an appropriate model. Now, before you analyze, you have to idealize. To make your model, you're idealizing. So I have this saying that to analyze is first to idealize. So that's why this idealization and understanding what idealizations you've made, and then subsequently you need to try and validate your model. So the message I really wanted to get across is that modeling is very much more than simply carrying out an analysis. The process of idealizing in order to analyze is even more important than simply doing the analysis. The model can be conceptual, it can be very simple indeed, or it can be a physical model, possibly on a centrifuge, or it can be a very, very sophisticated numerical model. But in a sense, they're all part of this idealizing in order to analyze. The other thing about using the term model, which I like, is it emphasizes that it is an idealization of reality, and it demystifies analysis, because analysis can come across as a very mysterious, high-level activity, but it's a model. It might be a complicated model, but it's an idealization of reality. And then we come to the center, which is the empirical procedures and experience. And it will always be important in a subject as complicated as geotechnics, dealing with the ground. There is inevitably going to be empiricism. So much of our practice is based on experience with problems of one complexity or another, different types of geology. And I've used this word, well-winnowed experience, because too often I've asked, an engineer, why did you do this? And they come back from my experience. Well, is that experience really relevant to this particular problem? Is it well winnowed? Have you really understood this particular problem? So I think that's a very important aspect of our engineering, of our geotechnical engineering, is to be, in a way, quite rigorous about empiricism. You can be very rigorous about empiricism, and it's a very valid activity to indulge in. So I wanted to finish now with the one case record, one that I was deeply involved in, to illustrate the application of the geotechnical triangle. It's really the design of the underground car park at the Palace of Westminster, which is shown here, and sort of go through what was really key about it. When I was brought in, there was a decision they were going to use diaphragm walls around the excavation, and they were going to penetrate beneath the base of the excavation, which was about 18 to 19 meters deep, penetrate below that to stop upward seepage and so on. So I insisted that, one, we had to do quite a lot of sampling, and I think we sunk something like 12 boreholes, and I examined, destroyed all the samples. None were tested. Everyone was split and described, and the engineer was absolutely horrified. All this money had been spent on sampling, and there I was sitting there splitting them and examining it and so on. So what did I find? Well, the borehole, which you'll find there sunk all over the place here, could be summarized by this log here. So we have the standard sort of profile for London, with fill and gravel overlying the London clay itself. But and this was quite early on. I think you're all aware of it now. But each of these areas or aspects of London clay, or horizons in London clay, were all revealed in the log. But what was absolutely key, and at the time I'd never seen it mentioned in the text, in the literature at all, was that below what was really a heavily fissured but very intact London clay, there was a horizon of London clay, something like 15 meters thick, which contained silt and sand partings within it. Some of them up to 10 millimeters thick, and generally at about 50 millimeters spacing, these silt and sand partings. That actually came as a complete surprise to me. I'd not been aware. I'd always thought of London clay as being this wonderful, homogeneous, stiff, fissured clay that goes to great depth, and it's God's gift for building on. And that immediately waved a red flag, because the silt and sand partings occurred just beneath the base of this excavation, which and the floors of the excavation were proposed to be founded on underream piles. And I thought, right, you know, if we've got these silt and sand partings in the clay with the River Thames immediately next door, you know, what does that mean? And I'm not sure if it's on this slide or the previous one. I think it's on the previous one. No, it's not. It must be the next one. We did sink piezometers in the ground. There we are. And the water pressures right through, approaching what used to be called the Woolwich and Reading beds, were hydrostatic, in equilibrium with the River Thames. So we had hydrostatic water pressures in direct contact with the River Thames, with silt and sand partings under the base of the excavation. And I thought, crikey, Burland, you might, if you let this go ahead, you might well go ahead and succeed where Guy Fawkes failed. Because there's no question about it, the bottom would be blown out of the excavation if you didn't cut off any flow in. And that's really the key design decision, to take the retaining walls right down here to below the bases of the underream piles. That was all based on a simple but very careful borehole description. And this is what I mean very often. That's fundamental. It's absolutely key to the design. You can do the testing all you like, but that was absolutely fundamental. And I was also very concerned about the formation of these underreams in an area where there was silt and sand partings with flow coming in, because I think they could well have collapsed. So the point I really wanted to make was that the key design decision was based on a good ground description. And the last thing I wanted to touch on was there was a bit of analysis involved. I, with Ken Cole at Arups, had been involved in a couple of deep excavations around London, which we'd be foolish enough to make measurements on, which turned out to be very useful because we back analysed, we used those bits of measurements of movement to try and deduce the stiffness of the London clay, which was much greater than we were getting from lab tests, because lab tests in those days were between platens. There were no gauges attached to the samples, and they were giving very low measurements of stiffness. So we developed based our prediction using FE analysis, but linear elastic models. And so our predictions of movement, ground surface outside the excavation, were surface movements, settlements. We predicted a bit of heave by the wall and a subsidence trough of that sort. And in particular, Big Ben was founded round about here. So we predicted that it would tilt away from the excavation. And these were the predicted horizontal displacements. And of course, they were very useful for then measuring the likely tensile strains in the various buildings surrounding. So that's where the work was done. And then we made the measurements. And in many ways, the measured movements were very different from the predicted ones, in particular the vertical movements. Instead of this subsidence trough here, we measured a somewhat deeper one, just a little bit of uplift of the wall, but a subsidence trough very close to the wall and running back like that. So Big Ben, as it turned out, instead of tilting away from the excavation, tilted towards the excavation. And I pointed out to the Black Rod, I think, who was saying, you know, why had I predicted it going away? And I said, well, although I got the direction wrong, the amount that I predicted it would tilt is about right. He actually remained unconvinced. He didn't think much about geotechnical engineering at that stage. But what was lovely was that almost coincident with those results, Brian Simpson at Howitz had developed a lovely model, and he picked up that I think that's no. Yes, here we are. He developed this model with a very high small strain stiffness. So it's a non-linear stress strain curve. And almost at the same time as Brian did that work, developing that model, we at Imperial College were measuring local strains on triaxial samples, and we found exactly the same thing. You get very high stiffness at low strain, and then the material gets less stiff. So we're dealing with a non-linear material. And as soon as you feed that sort of model in, you get significantly improved predictions. And you can easily make this fit there, but you can see it's the right form of movement predicted by a non-linear model. So the field measurements helped to develop much more refined models. So we've been round this circle here. We use simple linear elasticity. We did monitoring. We compared the observed behavior with the predicted, and there's a refinement in the model. So we can go around that sort of circle there and develop more refined models based on making measurements and on your testing. And I think really that's all that I need to say at that stage, because I think that encapsulates the use of the geotechnical triangle and its application in a practical problem, namely the underground car park at Palace of Westminster. So I think that's all I need to say at this stage. Thank you.
Right, I'm going to be stepping back from what John's been talking about to what I was actually talking about in chapter 40. And I'm going to concentrate on how can we predict what the ground has in store for us. And I'm going to be doing a very, very snappy example of how we can get as much information about the ground before we even think about doing a ground investigation or making any kind of geological model. And I was taught when I went to GCG by Hugh St John to use a system called the TWA system. And I found it incredibly helpful. It's about topography, water, and anything odd. And what I also said in chapter 40 was about how much free information there is available online now. So there really is not much excuse these days from not having some idea about the ground before we even get as far as even thinking about doing a ground investigation or even having any kind of model whatsoever of the ground we can look at. For example, I'm only going to be talking about a handful of these sources: Google Earth, geological maps from the British Geological Society. Ignore all the ones that are in green. I'm going to be talking about the media. I'm going to be talking about how we will put that into the MOGE or the MOGE, how we basically back check things on what is a very, very useful set of books for this purpose. So I'm going to be talking now about Google Earth because it's a very underused resource in engineering to some extent. If you haven't had a play with Google Earth recently, please do so. Please go home and play with Google Earth. You can do so much with it and find out so much incredibly quickly. So from the point of view of the TWA model, what can you do? We can see this site, which I have outlined here. It's actually in Cornwall. I live in Cornwall. It's on the north coast near Newquay. Cornwall is the pointy bit to the west of the UK, in case you haven't been there yet. And we can see here quite clearly it's by the sea. What you can do in Google Earth is you can run your cursor over Google Earth live and you can actually pick up the topography. So you can basically move your cursor around. It will say that it's, in this case, 50 meters above ordnance datum up here. And then by the time we get down here, it's at about 20, 25. And then it's down to here at 12 meters. And then we get down to sea level down here. And that the topography over here, there's a valley coming through here. And there's a valley coming down here. So that makes sense. Our particular site is at about 20 meters above ordnance datum. We've got a site which again we can measure on Google Earth, which is approximately 21 meters wide at the top, 41 meters at the top, bottom, and about 70 meters long. Where's the water? The question about the water is about the beginnings of hydrogeological understanding of the site. In this particular site, we've actually said, or we've noticed that there is a stream that has caused this valley down here. And there's also a little stream that comes down here and feeds into that river down. It becomes a river by the time it gets to Porth. There is, because we're much higher here than these streams, we are actually quite a long way above the groundwater table in this particular area. So what are we going to say then? Oops. Too many controls here. We've got streams coming from the east towards the west, and we've got the sea towards the west. And that actually, in terms of risk, is the greatest risk for this particular project or piece of land. I'm not even going to say it's a project at this stage. And the only thing odd, well, there's a couple of things that are quite odd about this. There used to be, and the great thing about Google Earth is we can go back through time and look at remote data from as far back as it goes. Some of the images go back as far as 1945, which is when we have really good data from of photographs. But the satellite data dates from maybe about 2020, when you can actually 2000, where you can actually start distinguishing ground features quite easily. If we look back through these time layers, we can see that there was a hotel on this site and it was abandoned in about 2008. So that's a good question. The next question is, we've got an odd feature here on the coast. If you look at the coast, this is not a straight coastline. It's got, like, somebody's been in there with a hole punch and made little kind of roundy holes in it. And that is a bit of a giveaway in terms of maybe what's happened here. There may well be caves in the area. So we've got some questions. We've got a good start. I'm going to go back in time now to when the hotel was on the site. And I'm going to look at what the altitude is of the whole zone where the hotel was. It looks like a quite reasonable hotel. We can measure, as I mentioned before, the height above ordnance datum. They actually call it altitude in terms of Google Earth. And we can see that there's actually quite a steep top to the cliff in this area. So maybe that has something to do with what happened later. Now, Street View, you're probably quite familiar with in terms of Google Maps, but it's also part of Google Earth and you can access it for the same zone. So if you just click on the right-hand side, you can see a street view of your area. And here I am, nice sunny day in Cornwall. I can see that the road surface is actually quite nice. In a lot of places, you can pick up things like tension cracks. You can see if a road has been over and over and over again dug up and resurfaced. That's often useful information. It may not be anything that you know about at this stage, but it's a really useful piece of information. You can also find out whether anything else is happening. There's, for example, here, there's a drain which is got a new patch around it. Maybe there's some significance to that. There's a little bit of the site available here to see. What I would be looking for is there anything like tension cracks there? We're quite close to the edge of the cliff here. Is there any evidence of huddling or ponding of water on the surface up here? So we've got some more information. The road surface is okay-ish. Possibly the drain repair might indicate there's been problems, deformation of the drains in the area. We have no clear tension cracks, but it's one of those things that needs to be checked up. There may be puddling or ponding water, which is evidenced by just the sort of look of the ground. Then the next thing is the British Geological Survey sources. There's an enormous amount of information on the British Geological Survey, most of which we never actually access. GeoIndex is kind of like the entry level. How do we find out about the ground? Geology, quickest, right. Find GeoIndex, put in what you're looking for, which is usually, for example, Central London. We want borehole records. We want what are the superficial deposits? What is the bedrock geology? It's so easy. This is for the area we're standing on. When you actually go to a rural site, we have a completely different ballgame, which is why I chose this particular site. Here, we look that up and we find there are no boreholes in the area whatsoever, except in northern Newquay, but we do have the basics of the geology of the area. And if we right click onto this description of the geology down here, we can find by passing through various menus that we have got Bovey Sand Formation, slaty mudstones, sandstone beds, thin limestone beds. It's about 40 million years old. This is not London clay. This is something that was London clay a long time ago that's been squashed and squashed and squashed and squished. And this is different now. And it's been weathered. So boreholes a long way away, may be useful to some extent, but really and truly, we have got a snapshot. And for a lot of people, that is a really important snapshot. You will know 75% more than most people on a project if you know what the name of the formation is. Other things in GeoIndex, which again, please look it up and do mess about with it and look at the data that's available for it. Because it not only has in things like coal mining, it has radioactivity, it has all the things that you would like to know about vast areas of the UK, but were too afraid to ask. In this particular instance, I've asked it to, because I know about geology in Cornwall, I've asked about mines and quarries, and I've asked it about the shoreline management plan. Mines and quarries in Cornwall, it's a historic mining area. Basically, we had lead, silver, radioactive minerals, all sorts of exciting things going on from quite a long time ago. So it's not unreasonable to find we have mines over here and mines up here within, a few hundred meters of the site. And there may be some historic mining in the area which may be affecting the site as well. So that's got to be something we've got to put in the risk assessment. The shoreline management plan, for example, is this green line. This green line shows what the anticipated erosion within the next 26 years is. And that doesn't look very good for the site, to be frank with you. So that is also useful information. So far we've got a basic geological model or ground model which is going back to the beginning of before what John was talking about. This is the absolute basics, that you're on the phone to somebody and you've just looked it up online. This is what we've got. We've got a site that is sloping towards the sea. There's possibly some ponding at the top. There may be some tension cracks in the top. That we know that this is what the geology of the area is. It's slaty mudstones, it's sandstone beds, it's got possibly some solution in the limestones. That there's some likely coastal retreat by the sea erosion of the cliffs by 2050 rather. And there may be caves. So we've got all of that information already just from going down this list of free sources. And then I wanted to know exactly what the ground profile is going to be. We haven't got any boreholes. There are no boreholes that have been done for this project that I've found so far. All I know is there's 7 small buildings that they want to build on this site. The plan is that they're going to fill the caves in with concrete, and it's kind of like, okay, so it'd be good to know what is actually there. Never been to this site before, but on Facebook, there is a fantastic website called Save the Whipsy Derry Cliffs, which is local people who are not happy about the fact that since 2008, this has been a completely clear area, and now people want to build on it again. So this photograph was on the site amongst a whole range of really other quite useful photographs. What can we see from this? We can see, actually, first of all, a lot of people down here complaining about things. We can see that this should have had a 3D drone imaging activity done in terms of the site investigation, and we will have to do that because it's a 3D problem already. It's not a nice flat cliff, it's a complex problem. Oh yeah, what's the crane for? There's a crane up here. What's that doing there? The crane, which is a 110 ton crane, is there to lift the 8.5 ton diggers down to the beach so that they can excavate where they're going to be filling in the caves, apparently with concrete. Yeah, quite exactly. So all of this information is in the public realm. What we can tell from this by drawing lines, and you don't have to be a geologist, but it does help. So find a geologist, show them the picture and say, what the actual, what is this? Well, we know these are rocks which were mudstones a long time ago, or were mud rocks, or were mud a long time ago, which have been squashed and then squashed and then squashed. What we can see is at the top, we've actually got a layer of sand, which is not unreasonable. It's quite common in Cornwall to have sand at the top. There's a lot of beaches and stuff around, and you get sand remobilizing easily. Then we've got some stuff here above which it has been weathered. It is a different colour. The colour is really important. As John was saying, it's an implication of a different material. Weathered rock is not the same as rock. It is sometimes extremely weak indeed. We have quite clearly here, we've got caves down here at the bottom. We've got an apparent dip, as geologists would say, of about 40 degrees. These rocks are dipping downwards towards the south. It's the south over here. But actually, when we start looking at the faults in the rock, and the faults are these little lines, there's a line here. I'll point them out in more detail. And actually, if we're looking at the faults in the rock, these are actually hitting into the rock like that, which means that these blocks, which have faults dividing them up, are actually pointing towards the beach, which is a different ball game altogether. So if we're looking at the lines we've got here, we've got faults, we've got too many. We've got some nice wedge blocks here which have failed. We've got the caves down here, which look vaguely as if they are there because the faults are there. We've also got preferential areas of the cliff which have been eroded where the faults are, which kind of implies that ground is weaker where the faults are. That's that, basically. So we've got potential risks, weaker zones near faults, wedge block failure, caves caused by undercutting from the sea. And also we've got a cave which has collapsed right next to it. So that's quite useful information. There are also some really good photographs which were taken by the protesters when these diggers were down at the caves trying to dig out some of the sand and then do some preliminary ground anchors or rock anchors rather. These are some cracks which were observed in the pillars surrounding the caves, and as you can see from distance they're quite a little bit unnerving, shall we say. If we look at them in a bit more detail, this is where that digger was, and these are the cracks coming down through here and then through this pillar down here, and you've got them over here as well. So glad to hear that the diggers were actually stopped at this stage and the works have not proceeded since then, which we can only be grateful for. Meanwhile, another source that you could be asking or going to is what's the weather been like during this process of the last few years, last few weeks associated with this site. You can go to the Met Office, which has got fantastic records from the last 100 years virtually. Just so happens I live not very far away, therefore I know that at the moment we have had 10 named storms in the last month and a half coming through Cornwall. We have increased rainfall and intensity of rainfall. We've had gale force winds, 40, 50, 60 miles an hour on a regular basis. That means we've got bigger waves coming in and hitting the base of this cliff all the time. And therefore the erosive energy that's being transferred to the cliff is quite high. This is a photograph I took in Penzance showing what are the average storms that we had over the last month. So far, in the process of 15 minutes, hopefully, I have found a lot about this site. From absolute basics, we know what the rocks are, we know what it's doing to some extent. We know that there's an overhanging profile on the beach, that we've got an undercut base. We don't know how big the caves are, we don't know where the caves go. All of this information we've gathered in hopefully 15 minutes or so means that we've got a very, very basic ground risk assessment before we go on to the stage of a ground investigation. This is the starting point of the beginning of John's triangle. However, this is what happened first. Whoop. This is in November, as you can see. So satisfying, so satisfying. And I want to ask you to think about this, is because a lot of people on Facebook have been saying, you know, could this have been avoided? Could we have actually, if we had known enough about the ground in the first place, and we've done a ground investigation, whether we could have predicted or avoided, I think we probably could have predicted, if we'd known more about the site. Frankly, after that first landslip, there were 2 more landslips within the next week. And if you look at the cliffs, you can actually see where the next landslips are going to be. So it's all I'm going to talk about now, and I would like to now hand you over to my colleague Tim.
And I'm going to talk about risk. Jackie's given a really good explanation of what not to do if you see a cliff failing. That wasn't Jackie taking the video, I hasten to add. And I think anybody in the room here would have stood a lot further back and see bits falling off a cliff like that, which is well-known experience, I think, or don't get squashed by falling cliffs. So thank you for the chance to speak. I'm probably doing the drier end of things. So chapter 7 is about geotechnical risks and the context for the whole project. It was written to try and actually help geotechnical engineers convey the issues that we face and trying to put the geotechnical risks into perspective. The first version was rewritten again with Marianne Walsh helping me, which is why thanks Marianne, who I don't think is here today. But I'm now going to talk about something completely different. So read the chapter. It's very good, I promise you, like the other 2 chapters you've heard about, but this is actually about managing uncertainty and managing risk in a general sense. So for any of you are geotechnical engineers, hopefully there's some more concepts that you might use. And for any of you who aren't geotechnical engineers, actually geotechnical engineering is a very good way of learning about risk. Geotechnical engineers are the best people for actually understanding. John mentioned sort of the gap of sort of God-made materials. We're dealing with wild randomness. We're dealing with things which actually can't be predicted. We're dealing with plots that only a geotechnical engineer will put a line through. So therefore, it's making sure that we understand and have humility about what we're dealing with. And probably actually humility comes down to a lot of what actually makes a very good geotechnical engineer, because there is no certainty. So managing uncertainty and achieving outcomes is actually critical to every project. If any of you read some of the stuff from the Infrastructure and Projects Authority, the IPA, and government, it's about outcomes on projects. And one of the outcomes people like is on time and on budget. And actually uncertainty is the ways of actually that doesn't happen. And the more you actually don't understand what you're dealing with, the more things are going to go wrong. So therefore, you extrapolate John and Jackie's really good explanation of how to manage risk into any other field of construction or built environment, and you'll understand now why we are the masters and mistresses of dealing with with uncertainty. So again, John explained about various things. I always liked geotechnical engineering because it's part science, part art. And it always will be. The sciencey part is actually edging further across and possibly further than it should be. But actually the art of understanding risk is absolutely critical. And the longer we do this, the more difficult it will be for AI to emulate us. And for those of you who are younger in the audience, it's running ahead of AI. I recognized when I started my career that AI and computers had the potential to come along and ruin my career at some stage. I've kept just far enough ahead of it so far in my career, and I think there's a good chance I get to the end without it. Those of you who are a lot younger than me in the audience, be really careful about this, because AI might overtake you. Make sure a computer is never more intelligent than you, is my advice to you in the room. And it's difficult as they're getting cleverer and cleverer. So provide value, earn your keep. And this comes from actually giving insights into actually things that are really difficult. I mean, Jackie's actually given a whole range of sources, but actually it takes an expert geological person, geologist, geotechnical engineer, to actually marry all those things together to get the level of insight that Jackie gave from the sources. But the level of knowledge is vastly better than when I started my career. The only way to do it is actually go to a site and have a look at things. At some stage during my career, actually, going to a site became a bit more optional. And I mean, Jackie didn't mention 3D Apple Maps, which I find absolutely fantastic, especially dealing with buildings and actually having full rendering of facades, which is, I think, another really, really good layer of information. We are responsible for project outcomes, for the geotechnical outcomes in the projects. You're responsible, and basically your curiosity, the ability to look at all of the sources, is about avoiding catastrophe. Somebody on this site planned to build something there. The fact that someone had knocked down a hotel on the site and decided it wasn't worthwhile at the edge of Newquay should have been a pretty good clue. However, somebody wanted to try and build something. And again, Jackie showed really quickly and really simply how it was absolutely bonkers. We've got lots of cases where you will inherit bits of information. And the example I'm going to give here is one I probably shouldn't talk about. It was a case where I was a geotechnical engineer looking after some data. I was about the 5th geotechnical engineer to work on the site, and the structural engineer about the 5th structural engineer to work on the site. Everything was actually lost in the midst of time. And there was an archaeological assessment called a site investigation for quite a major building being built. And it turned out everyone presumed that the archaeological investigation was a site investigation, and no one actually got one done. And construction has started. And I inherited this thing, and I thought, oh dear. I'm paraphrasing here loosely. Language may have been a bit worse than that. What do we now do? So me and the structural engineer worked out doing actually some of the really basic things that Jackie spoke about. What is the full risk of possibilities here? And actually it was a similar geology, but slightly different to what John explained. And what could go wrong on this 2-level excavation next to a grade 1 listed building? And tried to work out the full range of possibilities and concluded the critical thing was the depth between the gravel and the clay, because we had enough information probably to try and actually work it out. But fundamentally, this site had been looked after by lots of responsible people, but nobody had actually gone through and tried to understand that this archaeological setup wasn't a proper site investigation. The client got away without doing lots of boreholes, all the other stuff that should have happened on the way through. It was built very successfully, and I say we sensibly bounded the level of what was possible. But it was one where actually the process before us was diabolical, and everyone just presumed that what they had been given was actually accurate. So don't presume stuff. Go back to fundamentals, understand what you have, and go through it. And that's part of, I think, the art of a good geotechnical engineer geologist. As I said before, the outcome is what the client wants and needs. In the old days, it was on time and on budget. As geotechnical engineers, we're often told it should be cheap, but actually I'll highlight not too cheap, because everyone's going to try and drive down the cost, and you need to stand your ground and actually make sure that you get the right amount of investigation and knowledge to understand the uncertainty that we're dealing with. But fundamentally, what every client wants is no surprises. They want the thing to work, and they want resilience, but they don't tell you that. All you hear from the project team is, I want it cheap. But actually, and again, I've seen projects go horribly wrong, and some that I've been involved with, some I've come in across as an expert, and actually everyone gets very disappointed and upset when things go wrong and when the costs start escalating, and that's not a good place for anyone to be. And I'll touch on that a little bit more. We actually care very much about low carbon and climate change, and making sure we come up with solutions that are both low carbon in terms of construction and low carbon in terms of operation, how we mitigate climate change. We all know we need to achieve social value, and also we're looking at adaptation to the effects of climate change, which again, Jackie's case showed of the fact we're getting all these new storms coming through. I thought when this started happening and people started talking about climate change sort of 15, 20 years ago, it might not happen in my lifetime. We're actually now seeing it coming through quite shockingly fast in terms of actually how we need to adapt, and how and people are finding out what used to be a 1 in 100-year storm. You get 2 or 3 of them happening in 5-year periods at the moment, and that's not 1 in 100-year storm. But actually, statisticians and some hydrogeologists will tell you it is. So we need to actually be really alive to some of the facts that things are changing quite radically. And in the future, we're going to be dealing with a lot more about biodiversity and critical minerals, circular economy as a solution, lots of concepts that we need to be getting into. And therefore, I'm saying to the younger parts of the audience, it's a really fun time to be an engineer. It's a pivot time, and actually there's lots of new knowledge coming in that those who are a bit older are having to learn very quickly. So you can actually get ahead of us in some of these areas. The SDGs remain excellent and a really good way to get on top of some of the things that we need to try and achieve as a global society. So types of ground hazard, again, John and Jackie have alluded to them about overall ground risk. So if someone says, oh no, there's some people looking at contamination and there's an archaeologist over there, I really get annoyed, because actually as a geotechnical engineer, we should try and look at the whole thing holistically. Again, both John and Jackie's examples showed that. Just the fact that actually we're doing it, there's people with more knowledge than you about some areas, and that's great. But actually, we should look at all of the ground risks in the whole and make sure that we have an answer and understand the overall model. But also the way of dealing with a lot of them might be more holistic as well. And if you have a geotechnical engineer needing an investigation, a contamination engineer needing another different investigation, usually with very poor soil descriptions on them, and then an archaeologist going in with teaspoons and actually understanding a third level of investigation, that is not holistic. It's really good if we actually try and manage all of these risks together. And I've just touched again about some of the things. I mean, again, old foundations. I was involved a lot in how we actually look at these and actually convert them from being a hazard into possibly being an opportunity. And a SERI report that was written a few years ago. But actually, all of the things in the ground are levels of uncertainty that we need to get on top of. The book, the chapter 7 goes through different types of delays on public projects. Geotechnics is getting better from my day. There's less catastrophes than there used to be. There's still some pretty shocking ones, but actually overall we're getting into a better place. Again, when I looked at the data from before, about 20% of projects had significant delays due to unforeseen ground conditions. I think we are better now than we used to be. I think fewer projects are delayed by ground conditions. We found many other exciting ways to actually delay projects. Mechanical and electrical service has been a very popular one at the moment, and integration of design has been an even more popular one. But actually, you guys are the last dragon slayer. The dragon is still out there. The fact that the dragon doesn't come along and raid the village very often doesn't mean that it's not impossible. And again, Jackie's horrific example is a really good case of where someone can go in naively and not realize that we need to actually go and slay the dragons that everyone thought previously were sleeping. And again, one of the things in the chapter I wrote was actually trying to look at actually how much of a building is geotechnics. And basically, we look at maybe the site investigation, which is tiny in the overall scheme of things, the piling, the basement structure. Typically, on a modern London office building, might be only 7% of the building cost. And when you look at the overall building costs in terms of the economic output over a 25, 30, 40-year period, again, it's absolutely tiny. So if we actually stuff this up in some way, we're actually stuffing it up, saving a very small amount of money, but actually costing a huge amount of delay and everything else. So there's no cost efficiency in actually doing duff geotechnics. Doing a proper investigation is really, really cost effective. And again, the chapter explains that and gives you examples in more detail. And again, thank you for Pishan for actually helping me with some of this and actually putting some glorious Technicolor into my usual pretty inadequate PowerPointing. You think working for BCG would be better at PowerPoint by now. But basically, this just looks at sort of a standard process. And again, there's some really good data which shows the origin of geotechnical problems starts in the design phase or the construction phase, and then actually manifest themselves in construction and operation. But actually, there's lots of bits of this process that are quite useful. I mean, again, going back to John's phase of actually how we deal with the uncertainties and try and think about them. The choices we make in the design phase actually can increase the amount of uncertainty, as in dealing with the south coast of England's silty sands. Rafts are a really good solution and piles invariably go wrong. But all too often, if you ask a piling contractor for the solution, you end up with piles, even though it's so by asking a piling contractor to recommend the right foundation type, you are, by mistake, making a design choice that's going to actually go horribly wrong. So there's many pitfalls on the way, all the way through this in terms of what we do. But fundamentally, and again, having been involved in disputes and having seen some people effectively being destroyed as humans by really big geotechnical disputes, there's the direct repair costs, which usually aren't that big. There's a cost of delay, which geotechnics is invariably on the critical path, so are usually very big. The cost of dispute itself becomes really big. There's no money to actually do a proper investigation at the early stage. Once there's a dispute, there's hundreds of thousands of pounds available for extra boreholes and experts to opine on them mysteriously. But actually, the human cost is the bit that's probably the saddest and the most sort of troubling. Of actually, when something goes horribly wrong, people's lives, their careers are put on hold and sometimes actually very badly damaged. So overall, getting it right is really, really good. And again, this is just looking at the sort of the various project phases. And actually going back to John's point, which I can agree with hugely, the desk study, the time of looking at things, and Jackie gave a really good example of what we can do, is where we talk about hazard identification. If we don't do a good desk study at the very beginning, we will not have a good understanding of what happens afterwards. So a 10, 15 grand desk study pays huge dividends and is actually the time when actually you set the course of the rest of the project to go in the right way. Just like Jackie's bit of Facebook and Google Earth discovered a huge amount of insight about a site. A desk study is a really good way of actually making sure you start getting things together. High impact, low probability events are the curse of geotechnical engineering. I mean, again, Jackie discovered the mines, she discovered the possibility of the caves, and notionally, these are very, very high impact. But actually, if you don't know much about the site, you look at all the sites in Cornwall, you might think they're actually low probability. In actual fact, on the site, it's a high impact and very high probability event when you know what you're doing. But two books that are really good for people who want to understand risk. The Black Swan by Nassim Taleb is really interesting. And in it, he introduced the concept of randomness, which is a bit like uncertainty. And he speaks about wild randomness you get with these high impact, low probability events. And the concept of them is a really important one for geotechnical engineers for conveying the risk that we deal with. The Mervyn King books, for those of you who are slightly older than the target of this audience, of which there's a few of you in the audience, remember Mervyn King as the head of the Central Bank of England. And he wrote a book about radical uncertainty. And actually, most of it actually applies to geotechnical engineering hugely. So we come from this world of central banking and dealing with financial uncertainty to the world of geotechnical engineering and dealing with geotechnical uncertainty. And actually, most of the concepts are the same. Some of their banking ones are possibly more mature or less mature in some ways, but they earn more than we do. However, the issues they deal with and wrestle with are very similar. And he came up with the concept of the pre-mortem, which again, I'm seeing more and more used about things. Post-mortem is where you try and work out how somebody died. A pre-mortem is a really powerful concept to actually try and predict how someone or the project might die. And it's a really powerful technique to try and actually go through. I find doing standard risk tables, I'm going to touch on it shortly, really irritating. When you go through them, it's basically almost copy and paste from a previous project, really boring, and actually not the real risk in a project. If you say to somebody, how might this project fail? You come into some of the actual really good concepts that Jackie spoke about actually what this site in Cornwall might be. We all know Cornwall's had mining pre-Roman times, and Jackie found the mines right next to her site. So therefore, it's pretty obvious that mining might be a really big hazard there. But if all you do is cut and paste risk from a similar site, it might be another coastal site in Dorset or somewhere else, you might miss some of this level of uncertainty. Also in geotechnical engineering, perfect is the enemy of the good. We learned that in COVID, but I got reminded of it frequently. Trying to get perfect information very often distracts you from actually looking at the really good information you have in front of you. And again, as I get older, least bad is often more meaningful than best, I confess. In terms of risk complexity, a guy called David Hancock, who now works in UK government, wrote his MBA thesis and converted into a book called Tame, Messy and Wicked Risk Leadership. And he talks about actually different facets of risk and things that do with actually people come into wicked risks and people down to dynamic system complexity come into messy risk. And an awful lot of big infrastructure projects have got elements of both. So if I say to you, actually, what sank HS2, you might tell me, oh, a capricious government decision. Actually, it was really poor risk management, both on the wicked axis and on the messy axis of understanding all the things behind HS2's escalating costs. And again, I was quite saddened to see them actually blaming the old shibboleth of geotechnics being the cause of why it all went horribly wrong. But actually, I've yet to see any evidence of that myself. I think it's actually about poor risk management, of misunderstanding these deep systemic issues. So borrowing from Taleb's concept of randomness and uncertainty and actually risks, I mean, the whole consequence of tame and wild risks are, I think, really interesting for geotechnical engineers. Tame risks are easy risks. They've got linear consequences. They're things that you can actually deal with by contingency. So if something is linear and will not escalate hugely out of control, it's something that you can actually sort of manage much more easily. Giving you an example, if you buy a JCB to come and dig some holes in your site or hire one, and you end up with the wrong type of JCB. And there's lots of other JCBs you can go and hire or buy somewhere else. You might lose the cost of the JCB, that's all, and you might lose a week of time. But actually, you can get another JCB of a bigger size really easily to come along. It's just like a bit of inconvenience. If you buy the wrong TVM for Crossrail and you bore 2 miles into London and you come across some pile of foundations you didn't expect to find on your way, and there isn't a chamber for going and inspecting the front of it, you've got to rebore the entire tunnel or put a huge shaft down to go and investigate it. This will take years and will cost millions of pounds. This is sort of the consequence of making a small saving on the TPM very early, magnifies, and later on comes a risk that's going to cost you years and millions of pounds. This is wild randomness, wild complexity. And therefore, this, if you don't remember anything else from this lecture at all, the other ones hopefully you remember fully, but if you forget everything else from mine, just remember the difference of tame and wild randomness, and actually the importance in geotechnical engineering of getting them right. There's lots of current risk measurements, ISO 31000. I'm only mentioning it's actually mostly as geotechnical engineers, we ignore everything outside geotechnics. There's a very good standard. Risk is the effect of uncertainty and objective. Pretty good. Value of incomplete knowledge and organization decision making. I loathe the standard symmetrical risk matrix, which is why I got the X next to it, because it misses this point about wild uncertainty and the very high impact, low probability events. The risk matrix should be skewed and not symmetrical. The Orange Book is the UK government's way of managing risk. Again, lots of great concepts in there. RICS have written some really good stuff. IPA, Associated Project Management, National Audit Office. Lots of people delve into this area, and it is fundamentally misunderstood by all the various people. Fundamentally, at the end of the day, we manage the risk, but the client owns the final consequences. There are lots of examples: Deepwater Horizon, Crossrail. The client actually pays the price at the end if it's managed badly on their project. So therefore, visibility really matters, and mitigation of wild risk is really critical. So you mitigate them, you spend money in advance to deal with them. You don't wait for them to happen and possibly sink everything that you're doing. Also, a mild criticism of dashboarding. We see risk dashboards, and actually in a way it's a way of making sure that the senior people in the project don't have to engage with the dirty detail of managing them. Actually, the board of the project will deal with the consequences that come and bite them, and actually hiding that from them is really difficult, especially when you come into how things manifest. There's a really good article written about the failure of Crossrail in 2018. There's a website called London Reconnections. If you Google thermocline of truth and Crossrail, you come to the article. And the thermocline of truth means at the very top, you look down, for those of you who do diving, and you can't see accurately what's happening beneath you. And dashboards are very often reflect that situation. And when I discussed this with some major contractors, they said, oh yeah, we all know that. And they call us the watermelon principle on a project, which is green on the outside, but red on the inside. So basically everybody knows it's already failing, but actually the people at the top think it's all nice and green because no one's flicked the actual dashboard going into green. Traditional approach to dealing with risk are the APM talk about accept, transfer, reduce, avoid. There's the 4 T's: tolerate, transfer, treat, or terminate. Actually, you can either accept and manage a risk or actively reduce it. Transferring it doesn't work if you're the client, because actually you deal with the consequences one way or another when they happen. And actually avoid is really sensible, but actually can you do it too often? And I say in geotechnics, most geotechnical risks have got wild randomness. Therefore, mitigate, don't use contingencies. Again, in my BCG days, I was very fortunate to be allowed to take place in a research project on the shape of British construction and British infrastructure and why are we so late on doing everything. And actually the same principles apply in a way in some of these things, why and how to fix it. And we actually dealt with a thing called perverse risk aversion. And I'll just break those 3 words down. UK construction industry is massively risk averse, and therefore everyone goes for the most conservative solution, even sometimes when it's not the best one, and doesn't deal with risk properly. So basically it's perverse risk aversion. While you're trying to be averse to risk, actually you're increasing risks at the same time. And this is part of the reason why so many of our projects actually end up with being massively over-spec'd, because we actually don't get it right. So we can stop it happening. And again, I'm imploring you guys out there as really good geotechnical engineers of the future to actually go out and be allowed some of these projects and actually make sure we get these things right. You can avoid it happening by basically making sure people understand the risks on the project really clearly and understanding the consequences that might happen if you don't get them right. So be a great geotechnical engineer, preempt from experience and well-winnowed experience. It's only when I hear John speak, I hear the word winnow. I first met John in this building in 1986 when I came as a very young person about to go and learn an MSc here. But actually, well-winnowed experience is really good. Communicate is about negotiation with other people on the team and listening. Curiosity really matters. Curiosity, technical curiosity, all the things Jackie spoke about, but also about people, because these people you're going to have to negotiate with. You need to understand their perspective on things and what they're really upset about. And actually enable the best project team decisions. So mitigate the key wild risks, some of which are geotechnical, some of which might be other ways, and actually mind the gap to some extent. Make sure your bit finishes on time, on budget and efficiently, which means avoiding some of these risks coming and biting you. And I also think it's really good to extend our knowledge base in every project and also contribute to saving our project, our planet even. Thank you very much. So I'm going to leave you with John Ruskin quote, but I'm not going to read it out to you because it's too long, but you can hopefully, those of you who are younger can read this on the screen. So I'll leave that. Thank you very much for your time.
Wow, thank you once again to John, Jackie and Tim for a really engaging set of presentations. As always, time, cost, quality, we can only choose two. Obviously, this has been priceless and the quality of the speakers have been second to none. But we are running out of time, so I want to jump straight into discussion. I hope you remember using Slido and how we're using Slido online. There is a Q&A and there is a poll right at the end just before you leave to help us improve these future sessions. So if you've got any questions for the panelists, any prompters you want to get started with, anything about the presentations and also sort of the theme of today's discussion, please submit them. I'll kick things off to start with. If you have questions in the room, do put your hand up. We'll sort of go between Slido and the room, and I'll repeat the question for the online audience as well. Use mics, sort of pass them around as we, Got one up. Staff, just start in the room. Yeah, go for it. Yes, please.
Hi, my name is Staff. Thanks a lot. Great. First question is to Prof. Burland. Is there such thing as too much empiricism and perceived? And if there is, then how do we draw the boundary? The second question.
Can we just do one at a time? Sorry, Staff, just thanks. So the audience question was, is there, was to Professor John Burland, is there ever too much empiricism and how do we draw the boundary?
Is there too much empiricism? Is that, and how do we draw the boundary with, I suppose, analytical? I actually think that in the past there has been too much empiricism, because I don't think it's been well-winnowed experience. I think it's been just a statement of, you know, when I was on such and such a site, we did this. And I don't think it's been rigorously analysed. I do actually think it's a lot better. So I think that well-winnowed empiricism is great. They call it experience.
I'm going to also kick things off with a question of my own, if that's okay, because just to bring everything together, we've been trying to be very holistic in how we view geotechnical engineering, since sort of perhaps at the start of your careers, being a geologist or geotechnical engineer is perhaps even one and the same. It's an expertise to be in this industry itself. Whereas someone starting now, we only start sort of as a geotechnical engineer, and you're supposed to build your specialism in a very niche area and technical areas. And as Tim, you mentioned, in areas such as biodiversity and climate change. And so we no longer call geotechnical engineering itself a specialism. So how do you move between deep technical niches and deep technical knowledge, which you need, years of experience to build up to, but also have that holistic view that you emphasize so much throughout sort of the various presentations, so that we don't lose sight of either, but still be able to progress in one's career. If I can ask Tim to start.
I'll start, and Angus called a T-shaped person. So it's go deep and then go broad. And as you rightly say, Pishan, we need to go broad to understand, in a way, lots of other stuff. But actually, it depends on your personality and what you enjoy doing. I observe, for those of you who are younger, you have to go deep before you can go broad. A lot of people go broad, but then never go deep. I think it depends on what people want to do and we still need really good geotechnical engineers who do really good geotechnical analysis and design and not much else. But we also need lots of good geotechnical engineers who actually mind the gap and understand other things around them. And we need lots of people to work on projects. So you'll have your own personalities, you have your own things that inspire you, that you're curious about. And curiosity is absolutely critical in your career. I mean, so I would say stay curious all the way through. And actually, your curiosity might make you go down as a geotechnical engineer, genealogy works, or broader into other areas.
Generally speaking, it's considered that the best geologist is the person who's seen the most rocks or soil. But in terms of geotechnical engineering, it's not just about knowing more about geology. It's about the conversation that you were talking about. And I think one of the most important things that we need to understand is this communication process, the communication between different specialties in the area. The ability to understand somebody else's viewpoint, the fact that not everybody in the process of a project speaks the same language. And we need to really understand that as people in its own right. And listen to other people and listen to their own individual problems. The client's got their own particular way of looking at the world, looking at the site, looking at the ground. The contractor's got a different way. The geologist has got a different way, the designer's got a different way of looking at things, so a different perception, and that it's incredibly important that we get that tied up. It's that communication thing. And you don't have to be very experienced to do that, to actually listen and talk to other people. I think, and that is, for me, is one of the most important things.
And if John, if you had a...
I don't think I can add to that wisdom that we've heard, actually.
Yep. Hilary? Sure.
Lots of numerical models, we have automation, all sorts of processes that we're trying to deal with, as well as sustainability, new technologies, monitoring new systems, etc. It's a vast field, but I think that, for instance, the geotechnical triangle, if we just keep that at the core, we can see how everything's connected. We can, and the other thing is that we're in a scramble to get chartered and climb up the ladder, but geotechnical engineering is just a lifelong process of learning. So I think that try and keep hold of understanding what a sort of a core skill, soil mechanics, all the components of the triangle. Try and maintain that at the core, and see the other disciplines as kind of spokes going outwards of a wheel, And then you can see how everything's connected, and it doesn't matter if you don't really understand the full details of such and such a topic. If you understand how that relates to the core and you understand how the different aspects interconnect, then you can leave it to someone who wants to become a bit more specialist in that area, and know that you can go to them for advice. But they likewise will know who else to go to advice. So the important thing, and part of what this is all about, this series is to try and help us all maintain a sort of a core of geotechnical engineering, and with our colleagues, our geologists, that we need to continually be talking to each other. And I actually tried to draw this picture out, but it's a bit messy. But I have a feeling that it's a wheel or a sphere.
Yeah, thank you, Hilary. Just in the interest of time, we've got a couple of points online which I'll try and combine together. So I think the audience is quite interested in sort of how we're addressing issues of project cost overruns generally, how skill shortage play into this. If you know some of the presentations about you know a lack of risk management right at the start. And finally, how does the current civil engineering curriculum feed into how we're teaching the subject so that we're meeting the right, you know, demand in terms of skills, and if that can, you know, improve this race to the bottom for geotechnical engineering projects. If I start with Tim again at the end, that's okay.
And the industry is broken up to many bits, and we end up with some very, very, very good geotechnical engineering taking place on a number of projects, down to some pretty disappointing geotechnical engineering taking place on a long tail at the end. And I feel very sorry for people who deal with the long tail more often, and clients who are very difficult, impervious to reason. And what we do for standards, I mean, our processes are better than they have been, so therefore things go wrong less often. Equally, I think some of our solutions are less imaginative, and there's probably less fun in geotechnical engineering than there used to be. And that's both a good and a bad thing. But we have more standard solutions, better standards, and therefore people generally are on average more competent, but competence puffed up by standards. I think there's still a really good bit of fun to be had in geotechnical engineering as a career. The things that attracted me into it are still there, but actually it's probably more on Hilary's spokes rather than maybe in the core of actually all the new things that we're discovering and learning how to be better at. So what is a low carbon foundation? Not just basically let's just do a foundation the ordinary way. I think, like I say, things go wrong. Skills is a really interesting piece, but like I say, for those of you here, you're in, you're learning, and therefore you're curious, and therefore you're doing some of the right things to get involved at the better end of the industry. Broad comments. I mean, follow the interesting stuff. You don't have to necessarily always work with bad clients, which is pretty depressing if you have to.
Just for John, do you think the current way on the way you've set up how geotechnical engineering is taught, is that still applicable today for what you see as sort of people coming out into the industry, to your experience right the sort of at the beginning of your career?
Well, I'm not teaching right now, actually, but I'm retired. But I mean, I think that we have to remember that we're actually human beings first, and engineers second. And one of the things that I think we have to watch out for all the time, because I just listen to the media, we get so much of it. We've got to remember, we've got to be rigorous. We've got to be mercilessly rigorous in our thinking, and test everything. And curiosity is terribly important. Communication is terribly important, because we're working with human beings, and those are the aspects which I think we've all got to hold on to. But think rigorously, communicating clearly is terribly important. I've been dealing with medical issues recently, and the appalling communication that I've seen coming out of hospitals and doctors' surgeries really depresses me. So those are aspects of being human which are so important. I don't know if that's helpful.
Yes, it's really interesting. It's like the whole series of questions you've asked, but kind of leading on from what I learned in the health service, because the health service was my first job before I got into geotechnical engineering. I learned that the really important thing is that we need to recognise when something's going wrong, and that it's not just that we need to recognise if something is going wrong. We need to be able to stand up and say, something is going wrong, stop. Let's do this differently. And I would say to all of you in the audience, especially who are younger, that the courage you require to do that is enormous, actually. And that regardless of skill shortages, this is down to, I have a suspicion, I as a professional have a suspicion that just this tiny bit of this project is not going right. And it's time for me to stand up and say, excuse me, I'm only a junior, but actually, let's stop. Let's have a look at what's going on here. Because the person who notices that things are going wrong is the person who's in charge of changing things. So, kind of better.
Just to tie that point up with sort of decision making and people in charge with some of the questions surrounding the future of geotechnics, I want to go back to you, Jackie. So oftentimes we see on TV and the news people who make decisions, political leaders, they say we're going through a particular decision because of the data we see. Someone has convinced them with numbers. Do you think, for example, for your Cornwall cliff collapse case study, you mentioned, well, in retrospect, we could have easily identified the cliff was going to collapse. There's plenty of evidence. But is there, are we at a day and age now where we can say the data or AI or machine learning or some statistical analysis has told me as a geotechnical and engineer and geologist, I'm 50% certain that this is going to fail because I've done all of the, the ground model that I've built through the data I've looked at online. Do you think sort of that's the direction we should be heading down so that we can actually influence people who say, well, I need the numbers to make the decision?
Just that question.
Can I come in here?
Please do. Please do.
I spoke about AI, and my guess is in about 20 years' time, geotechnics might become a lot less fun because the ability to predict will be much better than it is at the moment. Fortunately, at the moment, it's absolutely rubbish. But actually, ChatGPT is becoming actually quite powerful in terms of its ability to predict, but prediction is a bit like it follows the law of what average people say, and therefore it's not yet giving wisdom, it's giving the average. But sometimes it can be incredibly good for finding lots of stuff. So it's a major step forward. At one day, someone will have an AI that can actually bridge across some of the really big, effectively unconformities in our knowledge. So the person who plans the SI and actually where the boreholes go, based on really good depth study, geotechnical insight, will set the course of knowledge. If it's someone who does contaminated ground and it's all on a standard grid, they will miss really important stuff. So there'll be some big uncertainties there. At the moment, AI is nowhere near predicting how that will happen. Again, the difference between sort of taking the nearest borehole and saying that parameters are or whatever, because actually I've seen people try and do that and think it's really clever, but actually it isn't, because actually it might be a totally different formation. It just is what's happening, a massive unconformity in knowledge. At the moment, AI doesn't bridge these things, but I think it will do in, call it 20 years' time. Holger Kessler probably knows a lot of them from BGS. Introduced me to some people in Singapore who are doing AI in geotechnics and said they have doing some really powerful techniques. And I was absolutely both terrified and fascinated by what they're going to be doing. And all they're trying to do with the AI is actually work out how to convert old borehole logs into a standard thing and get information off old boreholes, which we as humans are quite good at doing. And we've all done it as young geotechnical engineers. But that step will be done by an AI at some stage. So to some extent, and I don't know if I'm answering your question, Bishop, but I'm giving Jackie time to speak, which is always useful. I think it's really interesting of where computers and the whole digitization gets to and when digital becomes wise. At the moment, fortunately, it isn't, and it's not much better than when I was a young graduate, but it's getting there quite quickly, and bits of it have been bridged. But I may not have answered the right question.
As you know, I would still say, and I think John would probably say, that we still have to ground truth. And that's at the moment, and I think actually going into greater use of AI is going to be incredibly important, is that, you know, it's all very well giving a computer the option to do the interpretation for you, but unless somebody checks that back to what did you actually find in the ground and put that into the program, then you're not learning anything. You're just going off on a tangent and you're increasing risk. So therefore, at the moment, we need to be ground truthing and feeding that information back into the circuit.
I say about with ChatGPT. I did talk last week where I used ChatGPT to work out which civil engineers were leaders. They gave a whole range of them. Most of them weren't civil engineers. And it said they weren't civil engineers. It said Putin was a civil engineer, but then sort of he's a lawyer. So you need to validate lots of things at the moment, unfortunately. Just like I mean, whenever you try and buy a bike on Amazon and you buy one, and then for months afterwards tries to sell you a bike again. So fortunately, but we're on the way to more powerful techniques.
Are there any questions from the room? I've gone to this side, so I want to see if anyone that side. Nope. Okay. Yeah, at the front.
It was just an observation really on the old, the new and the future. What really struck me seeing that on the screen, perhaps a little bit more senior in my career, that we're actually gathering all of these things as we go. So it's not an either or. The further we go, the more we need to assimilate. And I suppose to turn that into a question, what does that mean for the sort of old debate about the generalist and the specialist and the super specialist? Thoughts on that?
Can I come to you, John, if you have any?
I mean, I think specialism is important, but I think the intelligent generalist is actually more valuable. I really do. I think a breadth of vision is absolutely vital. On this thing of AI, I mean, I've been trying to follow it. There are a couple of things about it. One is the development of autonomous motor cars and so on. The big question I always ask is, where does responsibility lie? And I've not had an answer on that one yet. And that worries me. But also following it is, there's no question about it, it's played a very important role already medically in diagnosis. And I think we've got, you know, I think we could learn from that. Then there's just one other saying which I must get out, because I first heard it in Paris conference in 1961, and it was Skempton. And in his presidential address, he said the following: "No amount of confidence by the engineer on behalf of his client will have any effect on the great forces of nature." And I've never, ever forgotten that. And I think that's something we should always remember.
He said.
Any? Is there sort of, I'll leave room for one final question if there is one. Yep.
How would you convey the value of investing in good ground investigation and information finding to clients reluctant to part with their money?
Chapter A7. I do a cost benefit ratio of sort of the average incidence of failures versus the average cost of a site investigation. I put an arbitrary reduction in. And it wanted an intellectual thought piece or play piece, but actually it convinces you pretty quickly that the average cost of a failure, once you start scaling in consequential losses, just goes massively out. So in the middle of A7, there is a sort of effectively a cost benefit ratio of skimping on a site investigation and paying 10 times the price.
So we can show it's a chapter, take it along to the client.
I'm sure we would love to continue this discussion, which is why there's 15 more sessions along the way with many of the other authors. These sessions are still in planning, but to wrap this up, and thank you very much again to the ECG committee who have helped organize this, all of the people involved, of course, Professor John Burland, Dr. Jackie Skipper and Tim Chapman for your presentation and your support throughout as well. And to keep in line with our sort of sustainable approach to things, I haven't printed out anything or bought a gift, but we'll be giving you a voucher for some houseplants, which we've tried to find a company who has a net zero pledge by 2030, because these things do take carbon to deliver, they carbon to grow in a sustainable way. And yeah, I'll send that to your inbox soon. And a final note of thanks to our series sponsors who are supporting us throughout not just this session, but the many sessions to come over the next year or so. I really, really hope that you found this interesting and useful. And particularly if you are using Slido, if you are on it now, please go to the poll section. There's space for you to give us some feedback, tell us how we can improve this, how to make future sessions better. And to start our next series, this is going to be in April. The dates and times are there. Again, this will touch on the chapters in the book related to fundamental principles of soil mechanics, but not exclusively those chapters as you've seen today. We hope to use that as just a discussion point. We could be talking about how we are teaching soil mechanics, how, what sort of knowledge we should be teaching these days, how it can propagate into industry. So hopefully you are the catalyst for the discussion and not just the chapters themselves. Again, we'll have the early career group host, Ricardo Soffoni, for this session. Session 3 will be not in London, so we hope to reach out to a broader audience as well. This will be up in Yorkshire, hosted by Emily Riley, and with panelists shown for session 3. So that wraps up really the MOGE discussion. Sales.
What's the right answer?
Sales pitch. Thanks for reminding me, Tim. So the more important pertinent question is how we should be pronouncing MOGE. So let's have a. So John, unfortunately, on this occasion, I think you have sadly been outvoted, and MOGE is the winner at 46%. So not a clear, it is a clear majority, but yes, MOGE is how we're supposed to.
Not mocking.
And finally, just for some final housekeeping and announcements from the ECG. We have several more events coming up. The next one is next week. This is key for all early career professionals who are looking to get chartered with the ICE. We'll have a mock professional review at the ICE on Tuesday, the 27th of February. It's your chance to come and hear a recently chartered geotechnical engineer relive, hopefully with experience, of a short part of their presentation and also the interview questioning from the reviewers. Please apply to the cooling prize, the 55th version of the cooling prize competition. Deadline currently is Friday, 1st of March. It's a prestigious prize for someone in the early stage of their professional career. More details can be found on the BGA website. And finally, the BGA's sort of prestigious annual ranking lecture will follow with another prestigious dinner. But for those who are not invited or at an earlier stage of their career and maybe not, part of a large table at the ranking, there will be drinks. Yes, Gary? We are still looking for sponsors for the post-ranking networking drinks, which is also a tradition for the early career group. And it's going to happen literally just below where the main lecture theatre is in the H bar here at Imperial. And that's it for this evening. Thank you very, very much. And for tolerating the overrun. Thank you for us. Thank you as well.